Hello, everybody. This is Dr. Zhang. Uh, I'm making this video for General Physical Science online class, Chapter 9, Atomic Physics. Normally, Dr. Hicks has a video for each chapter, but for some reason, he didn't have any for Chapter 9, so I decided to do a makeup. So let's look at the the PowerPoint slide. So again, there will be some questions for you to answer while you study this chapter. The answer can be found in the last slides, just like before. So in chapter 9, atomic physics, we cover a couple of things. So distinguish between different models of atom and knowing the name in each model and the scientist responsible for it. And finally, describe the problems of classical theory of light. So historically, it takes time for scientists to discover what is made of an atom. Okay, and it takes a couple different steps. And on the way, they have to modify their understanding based on the uh, experiment, new experimental results. So mostly, I think I will follow this kind of historic approach to learn step by step. And well, the classical theory of light has some problems, and that problem actually caused them to modify this model one more step. So just this is just a very another step for building up the correct model of atom. Okay. So this is how this PowerPoint slides are organized. We start from talking about different atomic models, and then we talk about this new idea about light, and then we make some correction to the model based on this new idea, which bring us to the most up-to-date model. So there's some review about charge. Just keep in mind the electric charge is a fundamental quantity, and then when you have a electric force, when you have electric field that can add electric force on the charge. So at the very beginning, so this is the idea about atom. At the very beginning, they didn't know that there was atoms microscopically. Everybody thought the matter is just continuous divisible, just can cut it all the way through. And then John Dalton was the first proposed the first generation model of atom. So basically, atoms are very small particles, so that you cannot see them normally. But you cut your material all the way, eventually you reach to atom. They're indivisible and uniform spheres, just like this. This 1807. After that, uh, J.J. Thomson discovered a particle called electron. So therefore, he proposed a different model based on the Dalton's model. He called Plum-Potting's model. Okay, so this is what the model looked like. Okay, so because the discovery of electron that has negative charge, and then the whole atom, as people know, is neutral. So there, Thomson proposed that an atom is made of like electrons and then spreading out in a positive charge background. So all the positive charge are uniformly distributed in the atom, and the electrons are like kind of the plums in the pudding. In the and So how did he discover this? This is actually the uh, experiment he did. So he produced rays using several different gas types in the cathode ray tubes. So essentially, if you apply a big electric field, you can produce a ray from this tube that has some gas in it. Okay, and this ray can be deflected if you put a magnetic bar around it. That means this ray is charged. So this is actually essentially this is a ray of electrons. So from there, people realize now there's something that have negative charge from the atom. Okay. Okay. But this model actually is not correct. Okay. Later on, the third step, okay, is from Rutherford. Okay. He in 1911, Rutherford proposed a different model. Okay. Well, this is the model that I'll show you the model first. Okay, this is Rutherford's nuclear model. Okay, in Rutherford model, the positive charges are called protons. They're not spreading out in the whole atom. They're concentrated at the middle. Okay, and then you have electrons as point-like particles rotating around this center core. This is kind of like a solar system. You know, this is the sun. This is a bunch of planets. This is actually, I think, the model that probably a lot of you guys have in mind from your high school science class. A lot of people still use this model. It's very convenient model to have. And to a large extent, it's correct. Okay, so how did Rutherford change it, get this new model? So actually, he did this very interesting phenomena. I mean, experiment. So basically, he put a very thin filament of gold, okay, and then he shoot alpha particles to this filament, okay. So this is represented by this here, okay. So basically, if you assume that the Thomson's model is correct, then because there's all the charges spread out, okay, so there's a charge everywhere. So there you would expect that when you shoot the beam of particles, they will be mostly reflected by the filament. Okay. However, uh, that's not what he observed. What he observed was, okay, most of the particles go through the filament as if there's nothing in there, like almost like empty space. And only a small portion of them was reflected. Okay. So from there, he concluded that the materials are not really evenly spread out on each atom. Okay, it must be that most of the mass are actually concentrated. Okay, so most of the space in the atom is empty. Okay, so if the alpha particle go through this empty space, okay, if you go through, no problem. Only when the alpha particle hit around this nucleus, then it is reflected. Okay, so this explains his film. It's a very, very famous uh, experiment. So this experiment pretty much set up our current understanding of atoms. Okay. So from there, he concluded that, I mean, doing quantitative analysis, he concluded the diameter of nucleus is about 10 to the negative 14 meters. And then the diameter of the outer electron orbit is about 10 to the negative 10 meters, which determine the size of the atom. Okay. And most of the mass of the atom is in the nucleus, like more than 99% is at the nucleus. Okay, so up to now, there's three different stages of the model of atoms we talk about, right? Starting from Dalton's model, okay, of a uniform sphere to Thomson's model of plum pudding model, and then finally to Rutherford's nuclear model, okay, which is our kind of like current model, okay. So a lot of you guys probably think this is the correct model, okay. To a large extent, it's correct, but there's some corrections we need to make, okay. So now let's move on to the next section. So let's talk about the problem, the theory of light. Okay, so classically we understand light as a electromagnetic wave. So it's a wave. Okay, and from this, okay, if you do an experiment, this is actually radiation of some material at very high temperature. So see, this is giving a piece of like a steel rod. So it looks like almost, see, in the middle, this is showing you like a yellow or even white color, while on the side is a red color. And all the colors showing up because really high temperature on the steel. So you don't want to touch the steel because the temperature is like a couple thousand degrees Celsius. So it's really, really hot. And this when the radiation of light coming out of the solid. Okay. So you can do quantitative measurements. Okay. And you can measure the wavelengths and then intensity from this radiation. Okay. This from the hot solid radiation. Okay. So notice that it depends on the wavelengths of the so at different temperature there'll be different, you can see different colors of this radiation. And then the higher temperature is, the smaller wavelengths you have, or higher frequency you have. So but the norm is like going as a spectrum, but roughly speaking the peak, okay, of this each temperature corresponding to some larger wavelength. So as you increase your temperature, the peak of this kind of radiation is getting smaller and smaller wavelengths. Okay, that means if you see the red color in the radiation, that means the temperature is relatively low. The higher temperature you get, the smaller wavelengths you'll see from this radiation. Okay. Okay, this all looks nice from the theory of classical theory of light, but it turns out that it's not completely. So this is another question you can answer here. Okay. Uh, Turns out that this is not correct. Okay, so we would expect that the frequency goes like this. Okay, this is the frequency and this is the intensity. So remember when you use wavelengths, it's actually going this way, but frequency is one over proportional one over wavelength. So you would expect the intensity go higher as the frequency go larger. Okay, but it was not what observed from experiment. The experiment observed that there's a peak and then it goes down. Okay, so the classical theory of light cannot explain the experiment here. Okay, so this is create a crisis to classical theory of light and to classical theory of everything. So, and then it's Max Planck in 1900 introduced the idea of quantum. Okay, to explain this experiment. So basically, he's saying that the energy is proportional to the frequency of light. I mean, they're up to a constant called Planck's constant. Okay, and this idea is actually the first step towards quantum physics, which turns out to be the physics that controlling everything microscopically, everything with atomic size or below. Okay. Uh, so anyway, so he proposed this theory, and with this theory, all the lights are radiated not as a whole wave, but as a light quanta. So lights are like particles called photon, and then they carry energy with it. Okay, so roughly speaking, the quantum physics idea is like this. So if you consider classical, like the energy can be changed continuously like this. Well, if you go back to quantum world, the energy cannot be changed continuously, but it can change only like one step after another step. It's kind of like person walking on steps. Like here, it's like person walking on a like continuous ramp. Okay. Okay, so another related problem of light is like traditionally we know when you shine a white light through a prism, it's going to give you the whole spectrum of different frequency or wavelengths of light. But it turns out that if you shine light to a spectrum that come from some special gas discharge tube, such as neon light, okay, then you don't see the whole spectrum, but you only see certain specific wavelengths coming out of it. Okay, so this cannot be understood by classical theory. So this would be the like kind of like a emission spectrum of certain specific elements. Okay, and so that all caused the the Rutherford's model need to be modified again. Okay, so basically now the new model is like this is the previous model, like electrons have circular orbits around the nucleus, etc., etc. But now they require that the electrons can have only certain size of orbits, and the electron's energy is quantized. Okay, and so that's what the kind of new model look like. So this is the nucleus, and then this is the orbits of electrons. Okay, but they cannot be any orbits. So they have to satisfy a certain number, like quantum number. Like this is n equal to 1 orbit, n equal to 2 orbit, n equal to 3 orbits. So whenever electron goes from one orbit to another orbit, it radiate out a photon with this energy and with the specific frequency. Okay, so this explains why you don't have all the frequency spectrum, but only specific lines. Okay. Yeah, this is kind of like planetary model, but it's not exactly. Okay, so you can use this is a Bohr's model. Okay. Okay, so this is another question you can answer from here. So with all of these, we finally reached to Bohr's atomic model. Uh, the so this is what it looks like. So you have a electron as a wave going around the nucleus, and then it has to be a standing wave. Therefore, they cannot be at any arbitrary orbit, but it has to be like the orbit specified by quantum number n equal to 1 or 2 or 3. Okay. So this wave is actually kind of like a probability wave. Okay. But okay, I mean, it looks like really like this. Okay. This is an electron cloud or in the hydrogen atom is the electron wave. So the probability of electrons is the most when it goes to this n equal to 1. Say, suppose this is n equal to 1 orbit. And then that means the electrons still have probability of going somewhere else, but the probability is really, really small. Okay. Okay, so I think that's finished this chapter of atomic physics. Again, this my lecture is not covering every detail of the slides, but I want to give you guys a kind of like a summary of what is covered. Okay, and especially this 4 stages of atomic model. That's the most important thing I think for this chapter. Again, I want to go back. The first stage was a Dalton's model. Okay, atom is a uniform sphere. Second stage is Thomson's model. Okay, it's a plum pudding model. Okay, so you have electrons that are like point-like particles, but they're like plums in the pudding of a positive background. Okay, and then third step is Rutherford's model. Okay, the nucleus model. Okay, nuclear model. So you have all the protons concentrated in the middle. We call it nucleus, and then electrons going around the nucleus, rotating around the nucleus. Okay, this model is actually pretty modern, and a lot of people still have this in mind. The last step is the Bohr's atomic model that goes to here. Okay, this is the Bohr's model basically. They're not electrons still rotate around the nucleus, but they do not rotate in arbitrary radius. They are rotated in some specific orbits characterized by like a quantum number at n equal to 1, 2, 3. Okay. Another picture to look at is this picture. Okay. Or this picture. Okay. Okay. That just the technical message I think for this chapter. Okay. Thank you for listening, and I'll see you later.